Our presentation is about the floating wind turbine. Me and my colleague are going to present each section. First, I'm going to talk about the first part, and then Flavie, my colleague, is going to continue with the second part. The title of this presentation is a robust and adaptive sliding mode nonlinear control for floating offshore wind turbines. Here you can see the presentation outline. First, here we're going to have some introduction, and then we are going to discuss about the control of actually floating wind turbine in region 2 and then on region 3. Due to the combination of wind and the wave disturbances, different dynamics applies the systems such as the aerodynamics, hydrodynamics, as well as the structural and servodynamics. So we can say that the floating wind turbine actually is a highly nonlinear system. Different platforms for floating offshore wind turbines are presented. Here you can see 4 of them: the starboard platform, the semi-submersible, tension leg platform, and barge platform. The advantages of using floating wind turbine is that having a strong wind off the coast with very little disturbance to the wind profile. This means that we can have a higher power range than today wind turbine. Floating wind turbines, or actually all of the wind turbines, are working on different working regions, on 4 different regions. The first region is region 1, in which the wind speed is less than the cut in wind speed. So it means that the wind speed is not enough to produce and gives us the power. So in this case, the wind turbine is just a stop. After that, when the wind speed is between the cut in wind and the rated wind speed, which is called the region 2, and the wind speed is not too high to gives us and produce the nominal power. In this case, we are looking to get the maximum power from the wind turbine. So the objective in this region, which is also called the low wind area, is to get the maximum power from this area. Besides, to keep the stability of the platform in order to reduce the fatigue loads. The region 3, in which the wind speed is between the cutoff wind speed and the rated wind speed, which is enough wind speed to produce and gives us the nominal power. The main objectives is to regulate the power at its nominal power, besides taking care of the platform stability. And the region 4, in which the wind speed is too high, which may damage the system, and the wind turbine is just stopped and no power is generated. In order to ensure the mechanical stability of the wind turbine, we have to look for some approaches. There may be other approaches, but here we propose to design robust and adaptive nonlinear sliding mode control for region 2 and 3. Let me discuss more about the concept of MPPT, or maximum power point tracking. According to equation 1, which is the aerodynamic power, we can take the maximum power based on the parameters Cp, which is the power coefficient. This parameter is a function of lambda and beta. Lambda is the TP speed ratio and beta is the blade pitch angle. According to the given figure here, we can see that which is the power coefficient versus the TP speed ratio lambda. We can see that the maximum value for Cp occurs when the beta is equals to 0. So in this case, we can say that our power coefficient in this area is just a function of lambda. In order to get the maximum power, in this case, as it's shown here, it just needs to keep the TP speed ratio at its optimal value. In this case, we can claim that Cp is at its maximum value, and we can obtain and extract the maximum power in this case. Here, this was the concept of MPPT and how we are going to design our controller based on this. At the rest, I'm going to talk about the modeling and the control design of the wind turbine for region 2. As I discussed, the wind turbine has a numerous degree of freedoms, to be honest with you, and actually it has 24 degree of freedoms. Designing controller based on that much degree of freedoms actually are not possible. This degree of freedoms including the platform rotation and translation, blade flap-wise bending modes, and tower foraft side-to-side bending modes, and other degree of freedoms. So in order to tackle with this issue, a simplified linear state model is derived from OpenFast. Here we take a 2 degree of freedoms linear model and we choose the rotor speed and the platform pitch angle. Equation 2 is the linear model that we consider. It's a linear model in which the parameters A, B, TG, and BD are calculated by using the OpenFast. However, this model has an issue. The main drawback with this model is that it's a linear model, and in order to control the floating wind turbine, we need to do the tuning for each operating point, which is very time-taking and it's not our desire. So we take a control-oriented model for the floating wind turbine as equation 3. It's a nonlinear model in which the terms f and g are unknown and bounded. And here the parameters u, which is the control input, and for region 2 is the generator torque. The control design. Here for our application to the floating wind turbine, we take our controller as equation 4. This is the so-called super twisting controller, in which at the first format and the version, the gains K1 and K2 if are taken as equation 5, which is the constant gain or fixed gain super twisting, where we can prove the finite time stability. And at the second, if we want to apply super twisting controller to our wind turbine, we need to define the sliding variable according to equation 6. And the reference value, I mean the omega star, is calculated based on TSR strategy and also adding the float. This is the TSR strategy, lambda star V divided by R. And the second part is the floating. Both of them makes the omega star or our reference value. If we want to use the fixed gain super twisting, we may face some problems because we know that the perturbation, bonds of the perturbation in practical systems are difficult to determine. Even if they are determined, they are somehow not easy. Even if they are determined, they are somehow overestimated. So the good and the best solution is to use the adaptive gain controllers. The concept of adaptive gain controller is to increase the gain when accuracy is not sufficient and to reduce them as the control objectives are reached. According to equation 7, the adaptive rules are proposed, in which you can see that K1 dot and K2 dot are a function of the sliding variables. The first adaptive rule, which was proposed by Yurish itself, is as equation 8 and 9. Here we can see that the K1 and K2 are adjusted dynamically, but before that we need to set some parameters. Here we have 6 parameters, or we can say 5 parameters, in order to tune our controller. The second adaptive rules, which is proposed by Taleb, is a controller in which we need to just tune 2 parameters in which we need to tune the parameters alpha, which is the gain rate, and the parameters epsilon, which is the targeted accuracy. This rule is acting as the sliding variable. If it is outside the targeted accuracy, it starts to increase the gain. But as it enters the targeted accuracy and reaches to our target, it starts to decrease the gain based on the second part. The other adaptive rule, which was developed by LS2Zen, is the self-tune controller, in which we need to tune one less parameters. Here, the gain variation parameters, which is the alpha, is set dynamically, and we don't need to set it manually. So, to have and to implement this controller, we just need to set one parameters, and it's the epsilon, or the targeted accuracy. And the last adaptive controller, which is recently proposed by LS2Zen, is the auto-tuning controller, in which all the parameters are set dynamically, and there is no need to tune any controller, and it is called auto-tune controller. Here is the block diagram of our controller, which is implemented on the floating offshore wind turbine. Here you can see on the left side, the omega ref is calculated based on TSR strategy. Then the floating feedback term is added, and omega star is made, and the sliding variable sigma is omega minus omega star is given to the controller, and finally the generator torque TG is given to the open test in order to handle the floating offshore wind turbine at region 2. Here is just the simple design of our controller. If we take the system as equation 16 and the platform pitch angle rate as equation 17, also the drive time system as 18, we take the sliding variable as equation 19, and we can see that our generator torque is obtained something like this, in which J0 is the inertia, which is announced by the manufacturer, and NG is our gearbox ratio. Omega dot star is the omega star, which is given by a differentiator, and U is the super twisting controller here. Equation 9 are the nominal values which are taken from equation 20, sorry. And here I'm going to show you some results about our work. In one of our work, we take these profiles, the wind speed profiles and the wave profiles, something like this, and we compare two adaptive controllers, the self-tune controllers and the ASTW controller, which was proposed by Yurish itself, and we compare it to the baseline controller. At the left side, you can see the generated power, and at the right side, you can see the power coefficient, CP. CP actually here is a criteria to show the efficiency and the reliability of our controller. As the generated or the given actually CP is close to the CP star, our controller has better performance. In this table, you can see the self-tune controller error is 3.84%, and for ACW it's 4.12%. It shows that the self-tune controller has better performance in achieving the control objectives. Also, the self-tune has a better performance in achieving the mean value of the power in comparison to the HTW and baseline controller. Here you can see some results about the structural loads on the wind turbine. The first one is about the tower base and the blade roots. These values are normalized with respect to the baseline controller. We can see that our adaptive controllers have better performance in comparison to the baseline controller. In some parts, the self-tune achieves better, especially on the blade root flap wise, which is 3% better. Also, you can see on the second figure, which is related to the mooring line forces, except for the FF1 and AF1, the super twisting controllers, especially the self-tune, the blue one, has better performance. Also, you can see the results about the platform motions, which is related to the stability of the platform on the last, and we can see that except for the roll on the other parameters, actually the super twisting based controllers achieves better. In an other work, we actually integrated the PMSG to the floating wind turbine and to the dynamic of floating wind turbine. We did this because we believe that PMSG has a higher efficiency in comparison to the other generator like the IFIG, and it has a reduced maintenance and higher torque density. Here's the block diagram for when we integrate PMSG into our dynamics. We can see we designed for VD and VQ, which are the voltages of V and Q axis current, and we have three different sliding variables: sigma IQ, sigma omega, sigma ID, and finally we have TEM, which is the electromagnetic torque. This is given to the open fast, and the reference value is calculated same as before. On the previous figure block diagram, actually I showed before. And here are the results for this topic. We have compared three different adaptive rules: the self-tune by Mirzai, the ASTR, which is the reduced one by Taleb, ASTW by Yurish itself, and we also take the backstepping controller in order to see how a model-based controller acts while we don't have much information about the model of system. We can see that the power coefficient error increased by backstepping controller. However, with the self-tune controller, it has a better performance, especially in comparison to two others adaptive controllers. Also, the self-tune controller has better performance in generating more power. About the motions or the platform stability, you can see that except for roll and roll rate, super twisting has better performance. Here the values are normalized based on the baseline control. This baseline control is presented by Enrel company, which is the first control applied to the wind turbine. And here is the other parameters related to the tower base or the blade root, and also the mooring lines. We can see that super twisting has better performance on the blade root flap wise, and the ACW, the adaptive control proposed by Yurish itself, has better performance in fatigue reduction, especially on the mooring lines. Actually, we have implemented all these adaptive controllers experimentally on the test tank at École Centrale de Nantes under very different conditions. But here I've selected some of them. And before that, I'm going to play a video about, you can see our test environment and how we have implemented these controllers. Okay, here you can see some of our results. Here I choose to show the HTW controller by Yurish itself under this wind profile. It was the torque which was generated, and here is the generated power and our rotor speed. And here is the result for the auto-tune controller. You can see the four different variables here, and here are the comparative results about the HCW controller and attitude controller. Here the values are normalized with respect to the HCW. We can see that our recent adaptive controller, which is the attitude controller, has a better performance in comparison to the previous adaptive controllers. Also, we have implemented our controller on a large scale wind turbine. Actually, this is a 25 megawatt wind turbine. It's an upscaled version of a 15 megawatt, and we reached to some results here. We implemented the STW controller and compare it to the Rosco controller. We see that the power error, it's quite clear that power error should be less. And we see that for STW controller, it's less than the Rosco controller. Also, the rotor speed error, which shows the efficiency of the controller, is better while we implemented the STW controller. And on the left side, you can see the figures which are related to the generated power. It should be 25 megawatt controllers, the rotor speed controller, blade pitch, and the platform pitch rate. This test was for region 3, however, we are looking for implemented it on region 2. Okay, it was the end of presentation for region 2, and for the rest of presentation, my colleague Flavie will continue for region 3.
Yes, I will just take over the... Okay, so know that Eshan has introduced you the control design for operating region 2. I will this time talk about the control design of floating offshore wind turbine in region 3. So in this part, I will briefly give you a reminder of the control objective in region 3 and the main challenges. And then we will see that based on modified nonlinear control-oriented model named Betty, how we design fixed gain sliding mode controller and adaptive gain sliding mode controller. These works are based on Dr. Eddie. This is the work of Dr. Eddie Basbas. And then we will see that how we design a neural network-based super twisting sliding mode controller, but this time on a modified control-oriented model named Homer. So as explained earlier, floating offshore wind turbine is a highly nonlinear system. And for region 3, there is the negative damping phenomenon which causes instability of the platform motion. So there is a need to develop adaptive and robust controller for this specific region. However, because of this highly nonlinear system, which most of the time the controller demands linearization, so the linearization of the system dynamics or the controller around operating points. Here, we want to achieve the control objectives in region 3, so the regularization of power at its rated value. We focus on region 3 with the negative damping phenomenon. And this time, for achieving the control objective in region 3, so here are the different control objectives, we want to use nonlinear control-oriented models that will be adjusted to synthesize the controller. So we don't want to use linearization around operating points. Indeed, when it comes to floating offshore wind turbine modeling, there is 2 categories. So the simulation model for the structure design, for example, but this kind of simulation model are analytically unexploitable. So for example, we have fast or open fast, and we have the reduced model, so the control-oriented model, which are not fully exploitable as it is, but with some adjustment, we can use them to synthesize controller. The main one as the Betty, Sumner, and Homer. In this presentation, we will see the Betty control-oriented model and the adjustment performed to synthesize the fixed gain sliding mode controller and the adaptive gain sliding mode controllers. Then we will see the Homer control-oriented model with the adjustments realized to synthesize the neural network-based supertwisting sliding mode controller. So first, let's delve into the modified Betty model. Here are the main characteristics. It's a two-dimensional model for a 5 megawatt tension leg platform floating offshore wind turbine. There are 6 states: the pitch platform angle, alpha, the source translation, epsilon, the if translation, eta, and their time derivatives. The control inputs are the blade pitch angle, beta, and the generator torque, t. Using this model and departing from the Lagrange formalism, we have this equation with a coefficient matrix of the mass and inertia, and x1 is the state vector, and f is the force vector with q epsilon, q eta, and q alpha generalized forces. And we have to reformulate this model to have a halving expression on the command beta. So we identify where his beta is appearing, and we have these three terms. And in the expression of these three terms, we have the q wind epsilon and the q wind alpha that use beta, so the command. For the expression of these two terms, we have the aerodynamic force given here, which use the CT, so the thrust coefficient, which is highly nonlinear in the command beta. And then we use this expression for the drive train, which use the aerodynamic power, and this aerodynamic power is expressed function of Cp, and Cp, so the power coefficient, is expressed with the command. So here is the formulation of the Betty model. And to be able to exploit this model, we are not using the classical expression for CP, but we approximate the CP and CT coefficient with a polynomial expression of two variables with degree 5. So here is the expression of CT and CP chosen here. And moreover, we had a first-order dynamics of the blade actuator given here. And finally, here is the adapted model. So based on this adapted model, a fixed gain sliding mode controller have been developed first. So the objective can be written mathematically with these two tracking errors, E1 and E2, where E1 is the regularization of the rotor speed at its rated value, and E2 is to ensure the mechanical stability with reduction of platform pitch rate. The sliding variable is defined as follows and can be rewritten as sigma 1 equals C1 E1 plus C2 E2, with C1 and C2 two constants. So using the second derivative of the sliding variable is equivalent to have the second derivative of E1 and E2. So first, the second derivative of E1 is given here by the expression with F1 and G1 expressed as follows. And we use the polynomial expression of Cp. And considering the external disturbances, the parametric uncertainties, and unmodel dynamics, here is the final expression of the rotor speed dynamics second derivative. And the same procedure unfolds for the platform pitch dynamics. So here is the expression. And with the polynomial expression of CT and the derivative of the different forces of the Betty model, we have this expression for the second derivative of E2. Finally, we have the second derivative of our sliding variable expressed as follows with F, G, and D given here. And it's a second order system. And we have the assumption of the bounded. 4 different algorithms have been used. So first, for the super twisting algorithm, because we need a first order, we use this auxiliary sliding mode sliding variable. But for the other 3 algorithms, so the continuous twisting algorithm, the Ding quasi-continuous algorithm, and the Ding discontinuous algorithms, we can use directly the sliding variable as it is. with respect of the assumption. For the simulation result, here is the wind and wave scenario used, and we have a wind speed, a mean wind speed of 18 meters per second with 15 percentage of turbulence. And here is the simulation results. So for the DDA, so the dim discontinuous algorithm, the performance was not great, so it's not represented here. And we can see that the three controllers can achieve the control objectives, but for example, the CTA, so the continuous twisting algorithm, show more oscillation notably for the control inputs. But the super twisting algorithm is the one that performed better than the three others. Here are some more data on the results. So here we also compare the super twisting algorithm and the three other algorithm to the GSPI, the gain scheduling proportional integral algorithm, which is the controller, the reference controller for the floating offshore wind turbine. So the fixed version of the super twisting algorithm meets the control objective better than the reference controller GSPI. However, the GSPI has less impact on structure than the super twisting algorithm because of the chattering, which is more present on the super twisting algorithm. And the fact that the fixed gain algorithms presented require knowledge on the upper bounds of disturbances. This is not always easy to evaluate and obtain. That's why we wanted to synthesize adaptive gain sliding mode controllers that will free us from the need to know the upper bounds of disturbances. So this is the next part, the adaptive gain sliding mode controller. Here is the basic principle. So we have our system. Here is the nonlinear sliding mode controller, and we have the sliding variable and the adaptive gain L. Two adaptive algorithms are being studied, the barrier function and the Moreno adaptation. Okay, so first for the barrier function, here is the control signal expression, and we use the super twisting algorithm. And the adaptive gain expression is given here with the variation LPB for the gain. The controller parameter chosen are given. And for the simulation result, we use the same scenario of wind and waves. And here it is. So we compare it to the GSPY in red, which is the reference controller. And we can see that the barrier function super twisting algorithm is able to meet the control objectives and show less oscillation than the GSPY, notably for the rotor speed, the omega R, and the platform pitch angle and velocity alpha and alpha dot. Here are some more results. So we compare it to, it's still compared to the GSPY, and we can conclude that the barrier function super twisting algorithm outperforms the baseline controller GSPY in all control objectives. Now for the Moreno adaptation, so here is the expression, and this time we use it with the continuous twisting, so we call it MCTA, and here is the control signal expression with the controller parameters. For the simulation results, still on the same wind and wave scenario, we can see that even if the Moreno's continuous twisting algorithm is able to track the rotor speed, the rated rotor speed, there is the oscillation are more important, especially for the platform angle and the platform pitch angle, alpha and alpha dot. So it's not always better than the GSPY. So yeah, the MCTA reduced rotor speed oscillation at the cost of a larger pitch angle compared to the GSPI. So for the adaptive gain super sliding mode controllers, the barrier function show great result, the barrier function super twisting algorithm, but the sliding variable converge only to a neighborhood, and we have to assume infinite actuator capacity. For the Moreno adaptation, there are possible overshoots, but there is another Another approach that we can use is the neural network coupled with the super twisting sliding mode controller. So the neural network is used to approximate lump disturbances, and the super twisting sliding mode controller is used for robustness and stability. This time, we use the nonlinear Homer control-oriented model to design the control law. So I will introduce you to the modified Homer model. It's a three-dimensional model, which represents this time a 5 megawatt semi-submersible floating offshore wind turbine. The Betty one was a tension leg platform. Here we have a semi-submersible platform. And there is 16 states, 6 platform degree of freedom, the rotor and generator angles, and their time derivatives. For the assumption and the simplification of this model, we consider it as a single rigid body. So the wind turbine plus the third floating platform is considered as a single rigid body. We neglect the nacelle motion is neglected, and we use the dynamic of the drivetrain, the one mass rigid shaft model given here, and we only consider for 14 states. So the free translational motion, the rotational motions, the rotor azimuth angle, and the time derivatives. Of beta, the control input, so the generator torque is considered fixed. For the interaction between the wind and the floating offshore wind turbine, here the aerodynamic power is expressed as follows, and we have the CP coefficient. So to be able to synthesize control objectives, we need to reformulate the rotor speed dynamic and the platform pitch dynamic, the platform pitch rate dynamic, so omega R and omega. But because of the high coupling between these dynamics and the control input beta, we need to use polynomial expression of CP and CT to be able to use these two dynamics. So here we use just a sample. We use the power, the aerodynamic power, and we substitute the CP polynomial expression, which give us this expression. And considering the external disturbances, parametric uncertainties, and model dynamics, we have this final expression, which with HR being the length uncertainties and external disturbances, with the bound assumption. The same goes for the platform rate dynamic, with this time the aerodynamic forces and the CT coefficient, where we use the polynomial expression. So considering the external disturbances, parametric uncertainties, and model dynamics, we have this final expression with HY lump uncertainties and external disturbances. To develop a neural network-based super twisting sliding mode controller. Here we use the radial basis function neural network-based super twisting controller. So RBF is ST controller. The same composite tracking error are used, so for the regulation of the rotor speed and the reduction of the platform pitch rate omega 1. Because it's an under-actuated problem, we introduce the composite tracking error given as following, as presented here, and we use it as a sliding variable. The dynamic of the sliding variable can be rewritten as GS multiplying by beta plus HS, using the reformulated dynamics of the platform pitch and the rotor speed, with HS being the unknown lump disturbances. So the control law is given as follows. There are 3 components, with beta RBF being the neural network estimator, which aim to capture and compensate the unknown lump disturbances. Then we have the approximation of the neural network error for compensating the network approximation error. And you have the super twisting control law for stabilization and robustness. Here, adaptive laws for the weight of the neural networks and the approximation error, neural network error, is derived directly from Lyapunov stability theory. So here's the overall block diagram of the controller with the 3 components: the error estimator, the neural network, and the super twisting controller. So first, let's look at the error estimator and the neural networks. So for the node networks, we have two nodes for the input layer. So we take the sliding variable and its derivative. Then we have the input layer, the hidden layer, with the CAB between being the Gaussian parameter, so the center and width of the Gaussian function, and each activation node function of each node, it's a Gaussian function. And then we have the output, which is the approximation of the lump disturbances HS. Here is the matrix of the different hyperparameter of neural networks and the feed-forward expression. This neural network give us the RBF controller. Then for the RBF neural network estimator, we have the exact expression of HS given here. So W star is the optimal weight vector and epsilon star is the minimal estimation error. And we have the estimation of the lump disturbances. So taking the differences, we can have the neural network estimator of the error estimation for the neural network with the controller here. And then the super twisting algorithm. So here is the expression. And for the stability, so we replace our command by the three components introduced. And we have this expression that we choose to rewrite as follow for using this Lyapunov function, which give us these two adaptive laws for the weight of the neural networks and the neural network error estimation. For the simulation result, we use the same wind and waves scenario as presented before. And we can see, so in blue, it's the neural network plus super twisting controller. In red, it's just the super twisting, but with the same gain as the RBF the same gain as the RBF plus super twisting. And in yellow is the GSPI controller, so the baseline. We can see that our controller, our neural network controller, is able to have a better tracking performance of the rotor speed with less oscillation, and better performance for the platform pitch minimization. Yes. So to conclude this part, the model-based approaches enable formal synthesis of controllers with different proposed methodologies. We saw the fixed gain sliding mode controller, where the super twisting algorithm gives us overall better performance for control objectives than the baseline one. But there is no oscillation of gains and more chattering, and there is the upper bounds problem. So we look at the adaptive gain sliding mode controller, where the barrier function super twisting algorithm gives us better performance than the GSPI. And then we look at the neural network based sliding mode controller with the radial basis function super twisting, which allow us to have lower gains and to compensate for disturbance and stabilization and reduce shattering compared to fixed gain sliding mode controller and adaptive gain sliding mode controller. Thank you for your attention.
Long live India and France friendship.